Up next, we're joined by Hui and Jesse. Hui is a software engineer at Salesforce. Jesse is the co-creator and a project lead on the Argo project. Prior to co-founding Acuity, Jesse was the principal software engineer and technical lead for the Argo team at Intuit, leading the design and architecture of workflows, CD, and rollouts. Jesse was a founding engineer of Applitix, acquired by Intuit, building a platform to help enterprises run containerized workloads in the public cloud. Jesse received his BA in computer science and cognitive science from UC Berkeley. Welcome, gentlemen.
Thanks, Sarah, for the introduction. Hi, everyone, and thanks for joining our talk on how scalable is Argo-Rollouts, a cloud operator's perspective. My name is Jesse Suen, and I am an Argo project lead and from Acuity.io. And I'll give it to Hui to give a little bit of introduction about himself. Hui, you're muted.
Oops, sorry. Thanks, Jesse. Hi, everyone. This is Hui Kang. I'm a software engineer at Salesforce. I'm currently working on the adoption of Argo Rollout to our CI/CD infrastructure. I'm so grateful for being able to work with the Argo community and learn from so many talented engineers. Back to you, Jesse.
Thank you. Okay, so in this session, we'll be talking about Argo rollouts, specifically with respect to scalability. I'll start by giving a refresher on rollouts, how it works, why we want to measure scalability, and then Hui will go over his benchmarking utility and the techniques he used in results, which ultimately led to actually a performance fix that was implemented in the controller. All right, so just a little bit of background about rollouts in case you're new to the project. Rollouts is a progressive delivery operator for Kubernetes, which provides blue, green, and Canary update strategies, which are missing from the deployment resource. And if you're unfamiliar with the term progressive delivery is just the practice of incrementally exposing new versions of your application to initially like a small subset of your users, and then gradually larger and larger set of users. And the reason you want to do this is to prevent impacting your user base in case of some problem like a bug. And so if in case something does go wrong, you only have impacted a small subset of users. And Rollouts provides three basic pieces of functionality. The first is that it has two strategies, blue, green, and Canary. You can also, with those, you can perform things like A/B testing. Second, Argo Rollouts integrates with service meshes and ingress controllers and leverages their advanced traffic shaping abilities like percentage-based traffic split. And finally, Argo Rollouts integrates with metric providers to decide whether or not to automatically promote your rollout or roll back based on the results of your queries. These are the integrations that we support. There are two categories of integrations. There are the traffic routers. These are basically ingress controllers and service meshes that provide the ability to shape traffic. And then we integrate with metric providers, and these are basically time series databases that Rollout can query as part of an update. And we're always adding to this list. I think one call out of this is we do have a very flexible way to integrate with your homegrown stuff using the generic web metric provider as well as a job-based provider. So the way Argo Rollouts works is it's meant to be a drop-in replacement for a deployment. And it works exactly the same way as deployment in that it creates and manages replica sets for every new revision of your workload. But unlike deployments, Rollout has two strategies, blue, green, and Canary, that replace the rolling update strategy. Rollouts also modifies other types of resources like services, ingresses, service mesh resources in order to shape traffic. And as I mentioned before, it can query metric providers to assess if the update is going well and abort it if it's not. And one important difference between a rollout and a deployment is that a rollout does keep track of what it considers a stable version of your workload. And this is basically the replica set that the rollout will fall back to in the case that the update fails. So why are we trying to measure the scalability of rollouts? Well, as we start to see more and more companies investing in adopting rollouts as a replacement for deployments, they need to have, it underlyingly has like a different implementation. And so these enterprises need to build confidence and trust in rollouts if it's going to be running their production workloads. And even though we have a very comprehensive test suite which tests for correctness, till now we didn't really have a good benchmarking test for speed and scalability, which is just as important when you're running at a large scale. And so we need to perform these benchmarking experiments to help assure adoption that this solution will scale with them. Okay, so I'm going to go a little bit about the rollout architecture and then things to be aware of as we're doing these testings. So this is a picture of the different components of the rollout controller and also the resources that it needs to either manage or observe. And as you can see from the picture, the rollout controller is actually comprised of many subcontrollers, and each of these subcontrollers have their own pool of workers, which can be tuned and scaled independently from each other. And I don't think people often realize until seeing this picture is like how much extra work the rollout controller is doing compared to just a normal deployment, which is pretty much only focused on managing replica sets. The rollout controller needs to modify, as I mentioned, those networking resources. We have a CRD for analysis. You can run Kubernetes jobs as a metric provider. And the controller even needs to make things like HTTP requests to metric providers like Prometheus. And so because of all of this extra work, we need to observe how the controller behaves under load. So in case you've never seen a rollout, this is kind of a snippet of what a rollout spec looks like. The spec should look familiar to you because it should look like a deployment, except for the fact that in this case, we have a strategy called Canary in place of rolling update. On the status side, just like many other Kubernetes resources, there's a conditions list that lists various conditions of the rollout. Here, we're seeing that a rollout is in what we call an incomplete state. And in this case, it's degraded because the current replica set is failing to make progress. This is a state diagram of a rollout. A rollout has 4 main states. When a rollout is first created, or whenever it's not at its desired state, it's progressing. And this includes when a rollout is first created. And so progressing simply means that the rollout is trying to make progress towards this desired state. And typical way you enter this is when you start a new update, but you can also get into the state if maybe when your pod just restarts. Eventually, once the desired version is fully scaled and available, the rollout is considered completed. I also refer to this as fully promoted, or you'll also refer to it as like healthy. If you are in a progressing state, you can then enter paused, and this is usually caused by explicit steps in your Canary or blue-green strategy, which pause your rollout at a certain part of your update. And finally, you can get into error state, and this is often because maybe your new revision is crash looping, or it also could mean your analysis failed and the controller considered the update as failed. This is also referred to as degraded. So just to expand on completeness, because this is what we'll be using to measure controller performance. For a controller to be complete, it essentially means that the desired pod template is fully scaled and all of its pods are available. It should also mean that 100% of the traffic is going to that new version. And in the case of basic Canary, it implies that the older revision replica set pods should all be scaled down. So basically all traffic is hitting that new version. In order to get to a completed state as part of update, you should have completed all your Canary steps successfully, and also all analysis should have also been completed successfully. Once a rollout is considered complete, we mark that replica set as the stable version. And at that point, there's no turning back. You can't abort the rollout at that point. If you need to go to the old revision, you just reapply those old set of manifests and go through the normal update procedure. Okay, and so we're gonna now go over what actually happens in both the blue-green update as well as the Canary, starting with the blue-green, and we'll go through the timeline of events. So here's a pretty basic blue-green spec. You'll see you have to reference a service because this is the object that will modify to point to the new version when it's time to perform that cutover. But you can also specify analysis that happens before the cutover as well as post-promotion after the cutover. And in terms of like what actually happens, so we then we update a revision to version 2 in the yellow. And at this point, we'll start creating that replica set and scaling out to that desired number of replicas. Once those replica sets are fully ready, we'll start pre-promotion analysis. And this is before the service has been cut over, so no production traffic is hitting it. Once that is successful, we'll switch the active service to point to that new revision replica set. And then we'll begin post-promotion analysis. And finally, if that's successful, the rollout at that point in time is considered complete. And then sometime after that, we will scale down the old replica set, but that's just to bake in some time to allow some networking objects to kind of settle down, because it turns out if you scale it down too early, you might cause some 500 errors. With the Canary strategy, you'll see that it's different in that you have to specify a list of Canary steps. So these are all user-defined steps that you decide like how you want to shift traffic to that new version. In this example, we're shifting by 10% every time, and every time we increase the weight, we're running this analysis called success rate. And if you look at what the timeline of this example looks like, we'll initiate an update, and since the first step was to increase the weight, we'll scale up the pods, wait for them to be ready, adjust maybe the ingress or the virtual service, and then we'll perform analysis. And then we move on to the next step and kind of rinse and repeat. And this is very dependent on what you have in those steps. And then finally, when you get to the end of the steps, at that point in time, the rollout is considered complete. Okay, so now that you have kind of a good basic understanding of how a rollout works, we'll hand it over to Hui to go over his methodology and testing.
Sure. Thanks, Jesse. Yeah, so next I'll talk about our benchmark methodology. So in order to evaluate the rollout scalability, our benchmark methodology aims at answering these three questions. The first one is that what is the metric that allows us to measure and quantify the scalability of the rollout controller? The second question is what tool can we use to generate load to excise different aspects of the controller during rollout's lifecycle? And the last one is, does rollout add additional performance penalty compared to the Kubernetes native deployment resource, which has been extensively used to deploy applications in Kubernetes? Next, I will talk about our solutions to each of the three questions. So note that our methodology currently only consider the rollout controller. So that means we don't consider the analysis run during the update because the duration of the analysis job varies depending on the specific applications. Similarly, we don't consider the latency of pulling container images because of its network dependencies. So before we define the metric, let's first understand what a conclusive state for a rollout. A conclusive state is a condition that the rollout is not making any progress such that the end user knows what action to be taken about the rollout. A conclusive state could be successful or not. For example, if user knows a rollout is completed successfully, they can start letting the rollout serve requests or traffics. But if the rollout deployment fails, the user need to take some actions to fix the issues. In contrast, an inconclusive state is a condition that the rollout is progressing toward a healthy, a failed, or a paused state. So based on these definitions, in the rollout state transition diagram, there are three conclusive states: paused, completed, and error state. The only inconclusive state is the progressing state. So let's look at a simplified timeline of a rollout state change. First, a rollout is getting started, and its pod becomes ready. And then after the replica set reaches designed state, the rollout is considered entering a conclusive state and marked as revision 1. Before the rollout reaches the completed state, the rollout is in an inconclusive progressing state. So next, when the rollout is updated with a new image tag, the controller will bring up some Canary pods, and following the steps defined in the rollout manifest, the update can be paused to run some analysis job. In this case, the rollout state becomes paused. As we mentioned earlier, a paused state is also a conclusive state. Then, after either manual promotion or the paused duration is passed, the controller continues the rollout, the Canary steps, until the rollout reach another conclusive completed state of a new revision. So with that, we can define a metric called convergence latency, which is the time a rollout spent to reach a conclusive state. In other words, the faster the rollout enters a conclusive state, the more responsively the client tool, for example, kubectl status, Spinnaker pipeline, can infer rollout status. So what are the meanings the proposed metric has for evaluating the scalability? This metric helps us to shape up the requirement of the benchmark tool we're going to build. First of all, the tool can emulate users to generate loads to access state transition of the rollout object, like creating, updating the rollouts. Secondly, the tool must be able to calculate the metric of the performance after executing the benchmark run, as well as collecting resource usage of the controller, such as CPU and memory. Last but not least is that the tool can also be used to get some baseline data, which in this case, the built-in Kubernetes deployment controller, so that we can do a fair comparison between deployment and rollout workloads. So the benchmark tool has been built and implemented as a command line executable that takes some input from the user. One of the input is a template which specifies the rollout or deployment object that are to be created in the cluster. Other inputs is the operations that to be applied to the rollouts, like creating, updating the image of the rollout or deployment, or deleting. Finally, the load size of the benchmark run is set by arguments like the number of objects and the burstness. After user run the command, the load is generated against the Argo-Rollouts controller running in a cluster. Meanwhile, if the measurement feature is turned on, the benchmark will also watch the status change of the rollout to calculate the convergence latency and finally report some statistics like 90 percentile latency over all the rollouts or deployments. And the command line at the bottom shows an example of creating 20 rollouts in a burst and waiting for the metric to be reported. So we'll look at the demo video shortly. So this diagram illustrates a high-level idea of how the benchmark execution looks like. The benchmark run begins by spawning some child processes, and the worker threads or go routines, essentially. The worker threads are responsible for applying operations on the rollouts, and the number of workers is set as the burstiness of the load. And meanwhile, the tool also creates a monitoring process. And when the rollouts are getting created, they are added to the watch list of the monitoring process and inform the monitoring process of any status change until reaching a conclusive state. After all rollouts are in conclusive state or timeout is fired, the command will exit with reported metrics of the benchmark execution. So next, let me show a video about how the tool works. So we started the command to create 40 rollouts, and on the right hand side you can see those rollouts are being created and displayed in the Argo UI. And meanwhile, the monitoring process is monitoring the status change of the rollouts. So when the rollouts finish, the statistics are reported in the folder, and the folder's name is given through the command line. So in this case, the name, the date, and time of the benchmark. And inside the report data, you can see the CPU usage, memory usage, and some plots. And also the rollout statistics, as I mentioned, and the detail of each rollouts. And then we can update the rollouts by set up a new image. Again, this operation is sent to the controller as a batch. And from the Argo UI, you can also see these rollouts are being updated. A new pod is being created as revision 2. And similarly, the monitoring process is monitoring the status change of the rollouts. So finally, as benchmark is run, we can issue a delete command to clean up all the experiment object. Yeah. Okay. I think that's it. So now let's look at some experimental results of the scalability test and how we use the tool to fix a performance bug in the rollout controller. So we conducted the test in a 5-node Kubernetes cluster on AWS EKS. The Kubernetes version is 1.19, and we use Argo-Rollouts version 1.1. The application we choose is the Rollouts demo, which is a stateless web application displaying colorful bubbles on the based on the image tag. So the picture on the right is how the application looks like during an update. So in this screenshot, the stable pods are popping up blue bubbles, while the Canary version is the green bubbles. So as mentioned earlier, the baseline we choose to compare with Argo Rollout is the Kubernetes building deployment workloads. So throughout the experiment, deployment and the rollout use identical pod template in the manifest. And since the rollout API supports 2 types of update strategy, blue-green and the Canary, we will test both strategies. And for deployment, we use its default rolling update strategy. So finally, we will report the 90th percentile of the convergence latency for each experiment. So this chart compares the performance between creating deployment and Canary rollouts before the performance bug in the Argo rollout controller is fixed. In this chart, x-axis is the number of objects to be created. In other words, the burstness of the load generated by the benchmark tool, and the y-axis is the convergence latency over the objects, and the lower is better. As indicated in the graph, we can see when the burstness increase, the deployment controller, which is the green line, performs much better than the rollout controller, as it is like a relative flat curve compared to the rollouts curve. Also, we noted that increasing the number of worker threads from 10 to 20 of the rollout controller doesn't help in this case. This makes us think that there must be something wrong in the rollout controller's implementation. So to troubleshoot these issues, we look into the controller's work queue length between 10 threads and 20 threads and the burstness of 20. Theoretically, the queue length of using 20 threads should be half of that of the 10 threads, as there are more workers to take elements from the work queue. However, the results show that the queue length of these two cases are very close. So it is clear to us that the worker threads doesn't consume the item from the queue at the pace we expect. So after some discussions, we finally find out that the root cause is actually the controller used the default QPS, standing for quest per second, and the burst from the client Go library, both of which are set to pretty low values, 5 and 10, which causes the performance bottleneck. So to fix these issues, Jesse submitted a PR and further make these parameters configurable as flags in the command line. Now with the PR applied, we rerun the experiment, and now the convergence latency of the rollouts are very close to the deployment, meaning migrating from deployment to rollouts won't have additional performance penalty on the applications. It is also worth noting that varying the number of worker threads doesn't impact too much on the rollout controller performance, given a high value of QPS and burst. So the same observation is also applicable to the performance of updating the image of a rollout or deployment, as shown in this chart. Both the deployment and the rollout controller experience some noticeable latencies increase as the workload burstness increase, which means that no additional penalty is added by the rollout controller compared to deployment. So next, we compare the rollouts of two updated strategies, blue-green and the Canary. The top graph is about creating rollouts of these two types, and the bottom is updating the rollouts. As indicated in both graphs, blue-green rollouts are constantly slower to converge than the Canary rollouts. The performance gap actually is caused by two reasons. First, unlike Canary rollouts, blue-green rollouts need active service and preview service, and these two services need to be reconciled during the reconciliation period by the rollout controller. So when the benchmark created the rollout object, the controller doesn't create the pods until the services are created in the cluster. So this caused a delay to the convergence latency. In addition, it takes additional cycles for the controller to update the labels of the service, active and the previous service for the blue-green rollouts, which is not needed by the Canary rollouts. Therefore, to mitigate the issue for blue-green rollouts for certain, say, latency-sensitive deployment, a best practice could be to create the active and the previous services, or the rollout controllers can be improved, say, by parallelizing some updates. Okay, so to conclude, as Argo rollouts becomes production ready, benchmark results show rollout controller is as scalable as the built-in deployment counterpart. And benchmark tool is critical to both developing the controller and tuning performance in production environment. So the future work regarding the benchmark tool includes extending the tool to support more complex templates with external dependencies like traffic routing and also extended the benchmark to analysis controller, experimental controller, etc. So finally, we are getting approval to open source the benchmark tool and to share with the Argo community. With that, I think, thanks everyone. We are glad to take any questions.
Okay. Do we have any questions in the chat?
Yeah, so there are some questions, Jesse and Hui, over in your session chat. If you want to go ahead and go over there and answer some of those real time. Also, there's some questions in the CNCF Argo channels around y'all's session as well. So you might want to hop over there and answer those real time. And to our attendees, we want to thank you for sticking around and listening to that. That was pretty interesting stuff from the guys. We've got a survey over on the main channel. We'd love to hear how you're actually using the tool right now, what your plans are for the tool in the future, and then just feedback around the event itself and what you want to see for 22. So thanks again, guys. We appreciate your time. And the guys will be over in the chat to answer your questions shortly.